Hello and welcome to the Electronics Cooling webinar, Advanced Carbon-Based Thermal Management Materials and Applications. My name is Belinda Stashukevich and I'm the editor of Electronics Cooling. Electronics Cooling has delivered up-to-date information and practical articles on thermal management since 1997. This webinar is presented by Carl Zwebin, Advanced Thermal Materials Consultant, and follows up on the success of Carl's last webinar, Advanced Composite Thermal Management Materials and Applications, which took place in June 2013. Carl has directed development and application of advanced electronic packaging and thermal management materials for over 35 years. He was formerly Advanced Technology Manager and Division Fellow at GE Aerospace, where he directed the Composite Center of Excellence. Carl is a Life Fellow of ASME, a Fellow of ASM and SAMPE, and an Associate Fellow of AIAA, and has been a Distinguished Lecturer for AIAA and ASME. This webinar will be interactive. You'll be able to ask questions and answer polls, and we encourage you to participate. Take a look at the Go to Webinar navigation pane. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. And to raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 45 minutes, followed by a 15-minute question and answer session. This webinar is sponsored by Jones Tech. Jones Tech is a solution provider to improve the reliability of the electronics equipment, which includes, but is not limited to, EMC and thermal management. Now Carl will begin the presentation.
Hello everybody, it's a pleasure to be with you today. This is the third in a series of webinars on advanced thermal management materials. And in this talk today, we'll be focusing on a remarkable material, carbon. There are many forms of carbon, as we'll see, and the properties are quite outstanding. So we'll start with a brief introduction to the issue of thermal management. We'll take a brief look at traditional thermal management materials, and then we'll get into the discussion of advanced carbon-based thermal management materials. After that, we'll look at some applications, future directions, and then we'll summarize. We'll start with a poll question.
Thanks, Carl. We'd like to ask our attendees a question. What industry do you work in? Please select one. Aerospace, defense, industrial, or consumer? We'll give you a couple seconds to answer this question. Looks like we have majority industrial. Back to you, Carl.
As we all know, and the reason that you're here is that heat dissipation is critical both in electronics and photonics. But in addition, thermal management also involves problems related to thermal stresses, which can cause warp rupture, fatigue failure, creep, and premature failure. Big issue today in both aerospace and commercial applications is reducing size, weight, and power, and thermal management is critical in meeting these goals. This is an old slide that goes back to the 1980s, developed by the U.S. Air Force, and it just illustrates the thermal stresses arising from differences in coefficient of thermal expansion. One of the problems that thermal engineers are facing is that traditional materials are increasingly inadequate for many applications. They go back to the mid-20th century. They can impose severe design and weight limitations, and some are very expensive. In response to these problems or deficiencies of traditional materials, we have an increasing number of advanced materials, and talk today will focus on carbon-based materials. These materials offer conductivities up to 5,300 watts per meter Kelvin compared to 400 for copper. They all have low CTEs, low densities, and I emphasize that they are at various stages of development from R&D to large volume production. In my various consulting assignments and short courses, I find that a lot of engineers, especially younger engineers, are only familiar with copper and aluminum as thermal management materials. And this imposes significant limitations. We have a brief 45 minutes to cover the material here. I cover advanced materials in more detail in a series of short courses that I present for various organizations. And I have some papers that I'm happy to send you if you're interested. This webinar focuses on materials used in heat sinks, heat spreaders, and closures. We also find that thermal interface materials using advanced carbon-based materials are under development, but we will not be able to cover them in today's talk. This is another chart that goes back to the 1980s, an Air Force chart showing the levels of packaging, starting with the individual package, working up to the printed circuit board assembly, the enclosure, chassis, or box, and I've added a fourth layer, the support structure. And in all of those levels, advanced materials are being used. So let's take a brief look at traditional thermal management materials. Before we start, I thought I would show this slide, since we'll be talking about properties, and I think people often tend to take the material properties for granted. But I've been involved in a lot of testing over the years and also round-robin tests. And what you find is that there's often a significant amount of variation in reported properties. So here we have a paper by Grabner and colleagues in which they did a series of round-robin tests on CVD diamonds, silicon carbide, aluminum nitride. And if you look at the range of values from the minimum to the maximum, what you find is that that variation varies from a factor of 2 to 3. And I found that in my own work. So the bottom line is, don't take material properties for granted. Let's take a look at materials we're trying to package. These are semiconductors, ceramic substrates, and here we have their CTEs. And what we find is that the range is roughly 2 to 7 parts per million per degree Kelvin. So for our thermal management materials, we would really like to have ones that match this coefficient of thermal expansion range. If we look at traditional thermal management and packaging materials, at the top we have copper and aluminum. They have good thermal conductivities, but unfortunately very high coefficients of thermal expansion, 17 and 23 respectively. That gives rise to thermal stresses. We can turn to materials like Covar and titanium, which have lower coefficients of thermal expansion, but those materials also have very low thermal conductivities and are also almost in the range of thermal insulators, not quite. If we need higher thermal conductivities combined with low CTEs, we can turn to materials like tungsten, molybdenum, tungsten copper, molybdenum copper, laminates like copper, invar copper, and so forth. And with those materials, and many of which are composites, we can get thermal conductivities in the range of aluminum alloys, but we pay a penalty in high densities. At the bottom we have e-glass epoxy, widely used printed circuit board material, of course, which is really a thermal insulator. And if you notice the range of CTEs, again, there's 100% variation in reported values that I found over the years for the CTE of e-glass epoxy printed circuit boards. So in response to the limitations of traditional materials, new generations of advanced thermal materials have been developed and are continuing to be developed. And we're going to focus today on monolithic carbonaceous materials, but we'll also be looking at carbon-based composites. And so there are various types of composites which are listed here, and they were covered in the previous webinar, number 2. So what are the advantages of carbon-based thermal management materials? Extremely high thermal conductivities, up to 5,300 watts per meter Kelvin, which is over 13 times that of copper. They also have low coefficients of thermal expansion, and if we're looking at carbon-based composites, they often have tailorable coefficients of thermal expansion. Some have very high stiffnesses and strength, and some have, I guess almost all have low densities, certainly compared to copper. How about disadvantages? Big issue is higher cost for many of them, but cost is relative. It depends on the competing materials. Copper tungsten, copper moly are also fairly expensive materials. If you're starting out with new materials, there may be some development costs to implement them. There are issues with hysteresis and carbon fiber reinforced aluminum and carbon fiber reinforced copper. These are composites. Plating may require development for some new materials. If we're working with diamond-based materials, they're hard to machine. And galvanic corrosion is an issue for carbon aluminum composites. And however, plating can prevent this. Let's take a look at the structure of diamond and graphite in various forms. On the top left, we have amorphous graphite, which is unstructured. In the middle, we have ordered graphite, which is basically a series of layers of graphene sheets. Their graphene sheets are held together in the C direction by van der Waals forces, which are relatively weak. However, the in-plane bonds between the carbon atoms, which are in a hexagonal array, are very strong and give rise to high thermal conductivity and high stiffness. So on the right, we have the graphene sheet, for which two people won the Nobel Prize for work on the graphene, which is a hexagonal array of carbon fibers. Single wall nanotube is basically a graphene sheet that's rolled up into a cylinder, and so we would expect similar thermal properties. Finally, on the lower left, we have diamond crystal, another form of carbon. It's a face-centered cubic, and it has extremely high thermal conductivity, high stiffness, and of course very hardness. So let's take a look at some of the forms of advanced carbon-based thermal management materials. CVD diamond. CVD stands for chemical vapor deposition. This is a well-established thermal management material. It's been around for many years. And this is unique in that it is electrically insulating. That is, of course, a property of diamond. We have thermal conductivities up to 2,000 watts per meter Kelvin and low coefficients of thermal expansion. Unfortunately, it's actually too low. The goal is a range of 2 to 7. CVD diamond has a CTE of about 1, and that can cause tensile thermal stresses on cool down in semiconductors and ceramic substrates. But we'll see that there may be ways to deal with this when we get to the applications charts. It has been noted that there may be some directionality of thermal conductivity. Emphasize that there are a number of processes for making CVD diamond. They each produce different sets of properties. And some processes produce strongly anisotropic materials, which means properties vary with direction. And in that case, in-plane thermal conductivity can be as low as 11% of the vertical thermal conductivity. However, I emphasize that some forms are effectively isotropic so that the vertical conductivity is similar to that of the in-plane thermal conductivity. So the bottom line is don't take the CVD diamond for granted. Properties can vary significantly. In addition to the anisotropy, some forms of CVD diamonds show through thickness property variability. And an important issue to consider is that price increases with increasing thermal conductivity. So you want to have a good idea of what you really need in your application so you don't overpay. So here we have a summary of some properties of CVD diamond. In-plane thermal conductivities, 200 to 2,000. Vertical thermal conductivities in the same range. In-plane CTE, as I mentioned, about 1. Look at the modulus. It's in the range of over 1,000 gigapascals. And for comparison, aluminum has a modulus of 70. That's 70. And the density is 3.52 which is about a little more than a third of that, or maybe half of that of diamond, which is about 9. Industrial graphite. This is a graphitic material that has been around for a long time. It's a commercial material. Notice that it has a low in-plane coefficient of thermal expansion, thermal conductivity of 95 watts per meter Kelvin. So it's not an outstanding thermal conductor in itself, but it is a porous material, as the chart indicates here, and it has a low density. So later on we're going to look at a material made by infiltrating industrial graphite, this particular type of industrial graphite, with copper to form a composite. And we'll see we get much better thermal conductivity. Another commercial product, or products I should say, thermally conductive graphite foams. And interestingly, in this case, because of the structure of the foam, they have higher through thickness thermal conductivities than in-plane conductivities. Notice they also have low densities because they are porous, they're foam materials, and typical of many types of carbon, they actually have negative in-plane coefficients of thermal expansion. That's not a mistake. What it means is that if you heat them, the in-plane dimensions get smaller. Another graphitic material, pyrolytic graphite sheet. In-plane thermal conductivities, as you can see, as high as 1700 watts per meter Kelvin. Notice the vertical thermal conductivity, which is typical of many types of carbon, is extremely low. So some forms of carbon are highly anisotropic. There are issues with getting the heat into materials like this that we'll talk about later on. These materials, pyrolytic graphite sheets, have low in-plane thermal conductivities in the range of 1. Vertical coefficient of thermal expansion is 32, and we can see that we have low densities. 2.1 is the highest density here compared to 2.7 for aluminum. So we're getting a significant weight advantage compared to aluminum. Flexible graphite is another widely available commercial material. If we go back to traditional materials, exfoliated natural graphite being something that's dug out of the ground, exfoliated natural graphite has been used as a thermal interface material, abbreviated TIM, for many years. It's a highly anisotropical, flexible, foil-like material, and in recent years, I guess going back about 10 years now, it has been used as a heat spreader as well as a thermal interface material. The higher forms, or the forms of flexible graphite that have the highest thermal conductivities, are made by a pyrolysis process. They are not dug out of the ground and processed. So we have a range of thermal conductivities here in plane up to 1500. Through thickness, again, very low, 3 to 10. In plane coefficient of expansion is negative, as I mentioned, typical of many forms of carbon. And the vertical CTE is positive, 27 in this case. And we see again that as for many forms of carbon, or almost all forms of carbon, there's a big density advantage compared to even aluminum. The density here is 1.9 compared to 2.7 for aluminum. Another form of graphite that is well established in thermal management is highly oriented pyrolytic graphite. This also is a strongly anisotropic material with very high in-plane thermal conductivities, low through thickness thermal conductivities. It's a very weak material. It's brittle, and especially weak in the interlaminar or through thickness direction. Because of the weakness and brittleness, it's typically used in an encapsulated form, as we'll see in a minute. And the encapsulation material is probably, or is reportedly, decoupled from the highly oriented pyrolytic graphite. So you wind up with a surface coefficient of expansion that's pretty much the same as the encapsulating material. So here we have properties of HOPG. There are a number of trade names for this material. In-plane thermal conductivities up to 1,700 watts per meter Kelvin, and that's over 4 times the value of copper. Again, vertical thermal conductivity is low, only about 25. Negative in-plane CTE, positive vertical CTE, and low density compared to aluminum. This chart shows encapsulated highly oriented pyrolytic graphite, where the encapsulating material is AlSiC. And those of you who attended the last webinar will recognize AlSiC as a metal matrix composite consisting of aluminum reinforced with silicon carbide particles. So that is a metal matrix composite, and AlSiC has a big advantage in that it has a low density, low coefficient of thermal expansion. You can tailor the coefficient of thermal expansion by varying particle volume fraction. So here we have pyrolytic graphite with in-plane thermal conductivity, in this case of 1,300 watts per meter Kelvin. So that is acting as a heat spreader, transferring the heat in the XY plane. And so the heat comes down through the AlSiC into the pyrolytic graphite, which acts as a spreader. So you get an effective in-plane thermal conductivity in the range of 1,000 watts per meter Kelvin, 2.5 times that of copper. The vertical thermal conductivity depends on the particular design, how much pyrolytic graphite you have, and so forth. The in-plane CTE is basically that of the AlSiC, which is 8.0 in this case. The modulus of AlSiC is 188, which compares with 70 for aluminum. So we have a material that actually has a higher stiffness than titanium, with a density in the range of aluminum, in this case 3.01. This brings us to graphene, which is quite a remarkable material. This is a single layer of carbon atoms that are bonded in a hexagonal array. The single layer graphene has a thermal conductivity up to 5,300. That's a measured value. A modulus, again, of 1,000 gigapascals compared to 70 for aluminum. And notice the in-plane CTE is actually strongly negative, in this case -8. That's an interesting phenomenon that multiple layers of graphene actually have a lower thermal conductivity than the single layer, and that's due to phonon transport effects. This is a commercial product consisting of graphene or graphite nanoplatelets bonded into a paper, formed into a paper. In-plane thermal conductivity is over 400 watts per meter Kelvin. Again, the vertical thermal conductivity is quite low, but we also have the benefit of a low density. This is an experimental product. It's multi-layer graphene film. This is multiple layers of graphene, and it's available as a film, chip form, and in blocks. Notice we have an in-plane thermal conductivity over 1,000 watts per meter Kelvin. Vertical thermal conductivity is reportedly over 300 watts per meter Kelvin. That's a significant breakthrough compared to other forms of graphitic materials. Density is less than 2, so again we have a significant weight advantage. And that takes us to our second poll question.
Yes, thank you, Carl. Attendees, do you need materials with thermal conductivities higher than that of copper? Yes, no, or not sure? We got quite a few answers already. Looks like the majority, with 80%, is yes. Back to you, Carl.
Thank you, Belinda. And for the sake of completeness, I've included composite materials that are based on various forms of carbon and diamond. Some of these charts were included last time, but some are new. So to look at the types of reinforcements we're talking about, we have continuous carbon fibers, top left. On the right, we have discontinuous carbon fibers, and I put carbon nanotubes in the same category. Lower right, we have fabrics and braids, which are formed from continuous carbon fibers. And lower left, we have diamond and graphite particles and graphite platelets. In this chart, we look at the thermal conductivity, modulus, and CTE of various forms of carbon reinforcements. Natural diamond particles have thermal conductivities as high as 2,200. Notice the asterisk. There is an isotope of diamond that has a measured thermal conductivity of 3,300. We have single-wall carbon nanotubes, a theoretical value predicted by Smoley of 6,600. And we have a measured value of 5,800. Graphite nanoplatelets, which can be formed into sheets, in-plane thermal conductivity of 3,000. And as I reported a few charts earlier, single-layer graphene has a measured thermal conductivity of 5,300. Notice that the CTEs are all low and some are actually negative. Let's take a look at thermally conductive carbon fibers. These have very attractive properties for structural applications as well as for forming composites for thermal management. Above the dotted line, we have continuous fibers that have axial thermal conductivities as high as 800 watts per meter Kelvin. Below the line, we have discontinuous fibers with thermal conductivities as high as 1,500. The bottom material, VGCF, stands for vapor-grown carbon fiber. These are fibers made by a type of chemical vapor deposition process. They're discontinuous, but again have thermal conductivities up to 1,500 watts per meter Kelvin. One of the advantages of composites is the ability to tailor properties. So here we have composites consisting of aluminum reinforced with thermally conductive carbon fibers. Vertical axis is coefficient of thermal expansion. Horizontal axis is fiber volume fraction. And you see that we can, the lines are theoretical curves, and they provide guidelines for selecting fiber volume fractions to tailor the CTE, and we actually measured negative in-plane values for some forms of carbon fiber reinforced aluminum. In this chart, we looked at thermal conductivity of the same types of carbon fiber reinforced aluminum composites, and you see that we can get in-plane thermal conductivities in the range of aluminum alloys combined with the low in-plane coefficient of thermal expansion. Turning to diamond particles, this chart shows the coefficient of thermal expansion of diamond particle reinforced copper as a function of particle volume fraction. And you can see that you can tailor the coefficient of thermal expansion by selecting the particle volume fraction. In this chart, we look at thermal conductivity as a function of both diamond particle size and diamond particle volume fraction. So we see that whereas coefficient of expansion only depends on volume fraction, thermal conductivity depends on volume fraction of the diamond and the size of the diamond particles. And as you can see, top right, we can get up to almost 800 watts per meter Kelvin. This would be isotropic for relatively large size diamond particles. So that was an introduction to basically just showing how we can tailor properties of carbon-based materials. Let's take a look at some actual composites. Earlier we talked about natural graphite. which is a flexible foil-like material. In some cases, we would like to have a rigid plate, and one way you can achieve that is by bonding the natural graphite particles together with epoxy to form the rigid plate. This is a material called HS400 made by Graphite. In-plane thermal conductivity is close to that of copper. The vertical thermal conductivity in this case would be through thickness is lower. Negative in-plane CTE. Elastic modulus, that's not too shabby. It's about half that of aluminum and a low density. And we'll see that this material can be used for heat sinks, for plate fin heat sinks. Talked about thermally conductive carbon fibers. If we embed ultra-high thermal conductivity carbon fibers in an epoxy matrix and what we call a quasi-isotropic laminate, so for example, we'd have fibers at 0 and 90 plus or minus 45 degrees, we can get an in-plane thermal conductivity of 270, which is higher than basically all aluminum alloys. In-plane CTE is negative, low and negative. And an in-plane elastic modulus, which is 165, which is more than twice that of aluminum. And the density is only 1.8, which again is much lower than that of aluminum, which is 2.7. So this becomes a very interesting structural material when you need thermal conductivity and high stiffness and low density. And we'll see an application of this material later on. Earlier on I talked about industrial graphite, which was a porous material. And here we have, basically it's an electrode material that is made by infiltrating this porous graphite with copper. And we see an in-plane thermal conductivity of 175. Sorry, this is an isotropic, effectively isotropic thermal conductivity, 175, which is in the range of aluminum alloys. And we have the additional benefit of a low CTE and a low density. And this material has been used in some package base plates. We talked about carbon fiber reinforced materials. Here we have carbon fiber reinforced copper. These are discontinuous carbon fibers that have very high thermal conductivities. And you can see that we can get in-plane thermal conductivities higher than those of aluminum alloys, combined with a pretty good vertical thermal conductivity in the range of aluminum alloys, low CTEs, and densities that are significantly lower than that of monolithic copper. This is another metal matrix composite in which the reinforcement is our reinforcements are graphite platelets. And notice that we get in-plane thermal conductivities as high as 750 watts per meter Kelvin. Materials highly anisotropic, so the vertical thermal conductivity is pretty low. But we have the benefit of low coefficients of thermal expansion in plane and much lower densities than certainly copper, and even lower densities than aluminum. So big advantage in plane thermal conductivity, low CTE, and low densities. I want to talk a bit about diamond particle reinforced metals. I guess when I first heard people talking about reinforcing metals with diamond particles for thermal management, it seemed a little bizarre. Think of diamond as extremely expensive materials, and they are in fact relatively expensive. However, diamond particle reinforced cobalt, which is a metal matrix composite, it's also called polycrystalline diamond compact, has been used for many, many years in rock drills and saws. Notice the thermal conductivity is quite high, over 600 watts per meter Kelvin. Low CTE, extremely high elastic modulus, over 10 times that of aluminum, and low density compared to copper. So the point here is that diamond particle reinforced metals, in this case cobalt, are widely used commercial materials. And my argument is that if these materials can be cost effective in something as prosaic as drilling rocks, they certainly merit consideration in at least in high-end thermal management applications. So we're going to look at a number of diamond particle reinforced metal matrix composites, in this case copper. And as we've seen, we can get thermal conductivities, isotropic thermal conductivities as high as 800. We can get low CTEs that again are tailorable, and densities significantly lower than that of copper. Here's diamond particle reinforced aluminum. This is a commercial material. In the last chart, there were an array of different diamond and particle reinforced copper materials. Some of them have been commercial for many years. This is a commercial diamond particle reinforced aluminum composite in plane thermal conductivity. I'm sorry, not in plane, it's isotropic thermal conductivity of 500, significantly higher than that of copper. Low CTE, much lower than copper, which is 17. Elastic modulus, again, extremely high, more than 20 times that of aluminum. And a density that's somewhat higher or slightly higher than that of aluminum, about a third of the density of copper. Diamond particle silver. As far as I know at this point, there are no commercial sources of this composite. However, notice that with diamond particle reinforced silver, thermal conductivities as high as 983, close to 1,000 isotropic, have been achieved. We can again get low coefficients of thermal expansion, as we've seen, by varying the particle volume fraction, and the densities are significantly lower than that of copper. I guess the last composite is a carbon-carbon composite. This is a material consisting of a carbon matrix, in this case reinforced with thermally conductive carbon fibers. If we align all the fibers in one direction, we can get an in-plane thermal conductivity as high as 800 watts per meter Kelvin. So it's sort of functioning like a heat pipe. If we orient an equal number of fibers in the 0-degree direction and the 90-degree direction, as we would, for example, with a fabric, we can get in-plane thermal conductivities in the range of copper, 350 watts per meter Kelvin, combined with low CTEs and densities that are much lower than that of aluminum. And this brings us to our next poll question.
Okay. Attendees, do you need materials with low coefficients of thermal expansion in order to minimize thermal stresses and/or warping? Yes, no, or not sure? Give you a few seconds to answer. Looks like about 75% said yes. Back to you, Carl.
Thank you, Melinda. Finally, or I guess I should say next, I want to take a look at some applications in order to give you an idea of where these materials are being used. Most of these applications are production applications, but I will specify where they are still experimental. So we'll start out with monolithic advanced carbon-based material applications. Earlier on, I talked about properties of CVD diamond made by chemical vapor deposition, which has thermal conductivity in the range of 1 part per million per degree Kelvin. And that's actually lower than we would like. We want the range of 2 to 7, and that low coefficient of expansion can actually cause tensile stresses during cool down from solder operations, for example, that cause tensile stresses in semiconductors and ceramics. So here we have a product made by Diamond Materials in Germany, and they have placed cuts into the CVD diamond to make it flexible, and that has the effect of reducing thermal stresses. So there are ways to get around the CTE mismatch problem. I talked about natural graphite thermal interface materials. Here's an example, and that's basically intended to transfer the heat in the through thickness direction. However, in the last 10 years, natural graphite is also being used as a heat spreader in addition to serving as a TEM. So here's an example of a notebook computer with flexible graphite heat spreaders. Flexible graphite is now a well-established, widely used material, high-volume production. It's used in smartphones, tablets, and displays. As I mentioned earlier, there are many serious problems in the photonics arena. Photonics being example, an LED, light-emitting diode application. As most of you probably know by this point, LEDs are cooled primarily by conduction. They don't radiate heat as incandescent bulbs do, and that poses serious thermal management problems. Flexible graphite is now being widely used in a variety of LED applications. Here's an application that's I find quite interesting. This is a detector that's used in a collider, and for heat dissipation they're using highly oriented pyrolytic graphite, one type of manufacturer's product called TPG, thermal pyrolytic graphite, and they're also using pyrolytic graphite sheet to transfer heat. As I mentioned, heat dissipation is a major problem in LEDs, light-emitting diodes, and here we have an application where highly oriented pyrolytic graphite is attached to the printed circuit board to dissipate heat, and doing so increases the efficiency of the LEDs and increases output by a staggering 60%. So it clearly illustrates the importance of thermal management in some photonic applications. As I mentioned, highly oriented pyrolytic graphite is a rather brittle and weak material. It's typically used in an encapsulated form. In addition, because it is an expensive material, you want to minimize the amount that you use. And so here we have an application in which highly oriented pyrolytic graphite is being inserted into a complex enclosure, and it's being inserted where heat spreading is needed. Notice those large circles of aluminum. They serve a mechanical function and also serve as a thermal via to transfer heat into the highly oriented pyrolytic graphite. Another illustration of encapsulated highly oriented pyrolytic graphite. Here the encapsulating material is AlSiC, this aluminum composite reinforced with silicon carbide particles, and these products are cold plates and lids, and you can see a picture of the highly oriented pyrolytic graphite insert lower left. And that brings us to our next poll question.
Okay. Is weight or mass important in your applications? Please select one. Yes, no, or not sure. We're getting a lot of responses in. The overwhelming majority, with nearly 90%, said yes. Back to you, Carl.
Thank you, Belinda. Let's let's turn to carbon-based and diamond-based composite materials and applications. I showed a couple of these slides in my last seminar, but most of the applications here are new. This is a composite material consisting of natural graphite particles bonded together with an epoxy matrix to form rigid plates. And here we have heat sink, natural graphite epoxy plate fin heat sinks, which have a big advantage in weight compared to copper fins. Talked about thermally conductive carbon fibers. Here we have a printed circuit board cold plate, or also called a printed circuit board thermal plane or heat sink, and it's made of an epoxy matrix reinforced with thermally conductive carbon fibers. So in addition to having high in-plane thermal conductivity and low CTE, this material also has a very high stiffness combined with low density. One of the problems with fiberglass printed circuit boards, we can see on the lower left, if we have a die directly attached to the printed circuit board, we have a die with, say, let's say it's silicon with a coefficient of thermal expansion of 2.5 parts per million, attached to a printed circuit board with thermal conductivity in the range, in this case here it's shown as 17 to 19 parts per million per degree C. That gives rise to high stresses in the solder joints that can be overcome by use of an underfill, which is a fairly expensive process. On the right, what we have is a carbon fiber reinforced polymer layer bonded to the dielectric, which is the fiberglass printed circuit board. This acts as a constraining layer, and we can reduce the difference in coefficient of thermal expansion between the die and the printed circuit board. This approach is not new. We did this when I was at General Electric 30 years ago using a copper invar copper constraining layer. So that approach of this constrained printed circuit board material is being used in a spacecraft supercomputer, single board computer. And in addition, if you use thermally conductive carbon fibers in the constraining layer also is a heat path. Again, sticking with carbon fiber reinforced polymer, this is a spacecraft electronic enclosure made of an epoxy matrix reinforced with thermally conductive carbon fibers. The big advantage here is weight saving compared to aluminum. You get high stiffness and high thermal conductivity. These are experimental cellular telephone base station flanges made of copper reinforced with discontinuous carbon fibers. Here we have a whole series of components made of aluminum reinforced with graphite platelets, which again gives you in-plane thermal conductivities much higher than copper, combined with low densities and low CTEs. I believe I did show this chart last time, but I think this is a true milestone in thermal management, electronic packaging. We have an electronic enclosure that incorporates a metal matrix composite. The manufacturer does not specify the type of composite, but if you look at the patent does cite carbon-based materials. So what you get is you get an enclosure with 2.5 times the thermal conductivity of aluminum and a weight savings of 10%, which I think is a very significant achievement. Turning next to diamond composites, I talked about diamond particle reinforced cobalt being used in rock drills. We have that on the right side. And on the left, we have another rather prosaic industrial application, a diamond particle reinforced copper grinding wheel. And those grinding wheels also have been used industrially for many years. So again, these are rather prosaic industrial applications of diamond particle reinforced composites. Diamond particle reinforced copper has been used in laser diode heat spreaders for many years. This is diamond particle reinforced aluminum. These are production gallium nitride RF flanges, which are plated with a combination of nickel and gold. As I mentioned, diamond particle reinforced silver is at this point an experimental material, and here we have an experimental gallium nitride spacecraft package with a silver, a a diamond particle reinforced silver base plate. On the lower right, we have the thermal conductivity of copper tungsten compared to the thermal conductivity of the silver diamond composite, and we see additional material that's used because of its low coefficient of thermal expansion. Next, we'll take a look at getting out our crystal ball and trying to predict where things are going in the future. I think it's fair to say, and without much fear of contradiction, that thermal management will continue to be a problem both in electronics and photonic packaging such as LEDs. The trend towards 3D architecture adds complexity to the thermal management problem. As a result, I anticipate continuing development of new materials, monolithic carbonaceous, as we've seen, composites, and new thermal interface materials incorporating many of these carbon-based materials. If we look at reinforcements, carbon nanotubes and nanofibers with thermal conductivities as high as 6,000 watts per meter Kelvin. We comment on the carbon nanotubes. Results so far for thermal management have been disappointing, largely because of the many interfaces arising from the small size of the carbon nanotubes, and that gives rise to phonon scattering. Natural graphite platelets we've seen are already being used. They have thermal conductivities as high as 3,000 watts per meter Kelvin. Diamond particles, again, they are in use, 2,200 watts per meter Kelvin. And I anticipate the development of electrically non-conductive particles and fibers. Of course, diamond particles are electrically non-conductive. I think graphene in particular is very attractive. The thermal conductivity of 5,300 in a single layer certainly makes this an interesting material to look at. We do need thermally conductive electrically insulating materials. I think in time we will see those as well. And other new materials are possible. For example, there was a recent paper that predicts the thermal conductivity of boron arsenide as being greater than 2,000 watts per meter Kelvin. So to conclude, thermal management is a critical problem in electronic and photonic systems, and that consists of two main parts: heat dissipation and management of thermal stresses and warping. Size, weight, and power will continue to be critical. Traditional materials all have significant deficiencies, and in response, there are an increasing number of carbon-based materials, thermal conductivities up to 5,300 watts per meter Kelvin, low coefficients of thermal expansion, low densities, and applications are increasing steadily. Finally, if we look at the development of advanced materials, they go back to, well, the first work with advanced materials, new generation advanced material, was some work we did at GE back in the 80s with ALSIC. So that's roughly 30 years ago. In the history of technology, 30 years is barely the blink of an eye. So I think it's fairly certain to say that we are still in the very early stages of a thermal materials revolution. So I thank you for your attention. There are some sources for advanced materials here for you to look at.
Thank you so much, Carl. We'd like to have a call for final questions. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, www.electronics-cooling.com. You can also email us at info@electronics-cooling.com with specific needs, and we can direct you accordingly. Carl, here's a question for you. How do you deal with the low through thickness of flexible graphite and highly oriented pyrolytic graphite?
That's an interesting question, and what I have found is that the first thing to do is to do a detailed thermal analysis. The low through thickness thermal conductivity is an issue, but is not necessarily a showstopper. In some cases, the through thickness, even though it's low, is adequate to meet the particular heat dissipation requirements of a particular application. In the event that it is a barrier to heat dissipation, you can use thermal vias, and you may recall that I showed an enclosure using highly oriented pyrolytic graphite inserts that had fairly large aluminum thermal vias. So that is one way you can overcome the problem.
Okay. To what do you attribute the great success of flexible graphite?
Well, flexible graphite has been extremely successful over the last 10 years or so. The success arises from the fact that there are materials with thermal conductivities as high as 1,500 watts per meter Kelvin. It's a very cost-effective material. It's available in a variety of forms. You can buy it encapsulated with aluminum foil. The flexibility aids the manufacturing process, and the fact that it's been around for 10 years has given people a chance to become familiar with this material. Obviously, there is lead time involved in any new kind of material.
Are the materials covered in today's webinar machinable?
All of the carbonaceous materials, the 100% carbon materials, are relatively easily machined. Composites reinforced with graphite platelets and graphite fibers, thermally conductive carbon fibers, are easily machined. The only problem areas arise with CVD diamond and diamond particle reinforced composites. However, I showed you some pictures of applications like rock drill bits, which are obviously machined from diamond composites. So it's an issue, but it's not a showstopper.
Are the materials discussed in the webinar readily available?
Most of the materials that I've discussed in the webinar today are readily available commercially. The ones that are not, I've tried to highlight. For example, the diamond particle reinforced silver is an experimental material, but I think almost all of the other materials are commercially available. The other exception being single-layer graphene sheet, multi-layer graphene sheets, which are still experimental, although graphite paper is commercially available.
And one last question. Can you comment on the prices of the various materials?
Price is a tricky issue. It depends on, obviously, the size of the component, things like surface finish, flatness requirements, plating, production volumes, and so forth. The bottom line is the only way to get a good handle on price is to ask for a firm fixed quote.
Okay. We have received so many great questions that we'll try to address in the future. Carl, thank you so much for your time and expertise. Webinar attendees, if you have any more questions that we didn't answer here, please send us an email at info@electronics-cooling.com. A recording of this webinar will be available on our website, electronicscooling.com. We will also send a link to all participants shortly. Thank you for attending.